Okay, let's start. Welcome everyone. Today we have a talk by Oleg Lunin, and he will speak about supergravity excitations of stringy geometries. Please start.
Thank you. Good evening. Thank you very much for the invitation. As I mentioned to Dmitry earlier, this year actually marks 25th anniversary since I graduated from physics department of Moscow State University. So it's a great pleasure to be back, even virtually. And today we'll talk about supergravity excitations of stringy geometries. So this talk is based on a couple of papers listed here, as well as on a couple of projects which are currently in progress.
Who was your advisor at Moscow University?
Dmitry Vladimirovich Goltsov.
Okay. So he's also working on killing tensors.
Yeah, exactly. Yeah. Well, it was a long path, as you know. I was doing something else, and then I came to this topic. So let me begin with motivating this work. As we know, non-trivial geometries play an important role in string theory. We get some understanding of quantum gravity from black holes in various dimensions. We get insights into strong interactions with the ADA safety correspondence, and we get insights into stringy dynamics from integral backgrounds. All these studies involve propagation of strings on some non-trivial geometries. So in order to study dynamics of these geometries, we're interested in several questions. We might be interested in mass spectra of excitations. We might be interested in scattering amplitudes, or we might be interested in dynamics of topological defects, which are described by branes in curved spaces. So if you talk about excitations, they come in different varieties. Light modes, usually described by perturbations from supergravity multiplet, where you take a background and then you consider some light fields on those backgrounds. Then, as your excitations become heavier, one studies strings and branes in curved backgrounds or in background fields. And finally, if excitations become very heavy, then one needs to look at new supergravity solutions, because now you cannot look at excitation as just a perturbation. It should be a genuinely new background. That reduces to the old one when the excitation is switched off. So in this talk, I will focus on light modes, and I will study this perturbation from the supergravity multiplet. To analyze such perturbations, one needs to study systems of linear partial differential equations. Linear because we're talking about perturbations. And in the case of the black holes, the analysis is usually done using separation of variables. And part of this talk will be about extending separation of variables to new geometries and to new excitations. When we talk about integrable geometries, then sometimes separation of variables works, sometimes it doesn't. But even if it doesn't, one can extract spectra from various worldsheet techniques. And the second part of this talk would be about extracting such spectra without relying on separation of variables. So the goal here would be to demonstrate separation of variables for tensor fields in all rotating black holes in all dimensions, and to find spectra and wave functions on large classes of WZW models. So these are examples of integrable string theories. So as I already went through the motivation, we're going to study black holes, and we're going to study various integrable string theories. And when we talk about black holes, I will begin with a brief review of the known results in 4 dimensions. So there, separation of all fields has been known for 5 decades. But even then, it turns out one can say something new, and these new results will be used to extend the successes to higher dimensions. Then again, next part will be a brief review of Myersberry black holes in their symmetries. So these are generalizations of the curved black hole to higher dimensions. And after that, I will discuss full separability of vector and tensor equations. So we will start with these Myersberry black holes in arbitrary dimensions. We will introduce gravity modes, which are either vectors or tensors, and I will show that they're fully separable, and the problem reduces to solving some ordinary differential equations. And finally, I will talk about some progress towards understanding of gravitational waves. So then I will switch gears, and we will talk about supergravity excitations of the West-Zumino-Witt models. So in that case, as we will see, separation of variables also works, but only in some low dimensional cases. And in particular, vector excitations in those cases can be obtained by relating various Vezzo-Minovit models by T-dualities. So this eventually will lead to spectra of scalar and vector fields in this separable case. But I will also talk about the finding scalar and vector modes from a group theoretic construction. So in low dimensional cases, this will essentially recover the separable results, but beyond this low dimensional cases, it just gives a new technique which does not rely on separation of variables. And these results also have some extensions to lambda deformed backgrounds. So as we will see in this process, there are actually similarities between separable modes of black holes and WZW models. And these similarities will be discussed as well. And then I will conclude with some outlook. So the first part of this talk will be about excitations of rotating black holes. And as we know, particles and fields provide insights into nature of black holes. So here are just some pictures from some relatively recent discoveries. So on the left, it's the picture from the first observation of gravitational waves. On the right, it's the first real photograph of a black hole. And in both cases, we get insights into the structure by studying excitations. So on the left side, it's about gravitons or gravitational waves. On the right, it's about photons or electromagnetic waves. So both these cases deal with classical radiation. And in classical theory, we might be interested in radiations from infalling particles. We might be interested in gravitational lensing or in gravitational waves. So in order to study all these things, one needs to solve the equations in non-trivial background of black hole. When we talk about quantum fields, we can also get detailed study of the Hawking radiation and detect the difference between black holes in its macro state by studying various fields. And then we can also test the ADS-CFT correspondence. Many excitations of black holes have been studied in the past. In particular, all fields and static geometries can be solved by using the power of rotational symmetry, as I will review later on. Essentially, all equations reduced to just a system of ordinary differential equations. Scalar fields in all dimensions have always been also been studied, but relatively recently, about 15 years ago, as opposed to the story of spherical symmetry, which was known for more than 40 years. And also electromagnetic fields and gravitons in 4 dimensions were fully understood. So these are the known results. And the goal of this work is to find the most general solutions for photons and higher forms in all dimensions, demonstrate separation of variables for gravitational waves, and understand the role of symmetries in that separating procedure. So we will see as a result that all separations are controlled by eigenvectors of the Killing-Yano tensor. Okay, so let's begin with a discussion of electromagnetic waves in geometry. Some of this will be overview, but some of the results would also be relatively new. So if you talk about the Schwarzschild geometry, then the symmetry is sufficiently large to ensure that all fields can be expanded in spherical harmonics. And as a result, regardless of the spin of those fields, one finds a system of ordinary differential equations, and all functions are of only one variable t, only one variable r. So here we have dt, the time translation. We have the rotations on the sphere, and that's what allows one to reduce things to ordinary differential equations. So more formally, and this more formal thing will be needed later on, more formally, we can see that the time translations and the rotations on the sphere are encoded in this equation for the Killing vector. And so in particular, this is the Killing vector corresponding to time translations. And because of the Killing vectors, one gets separation of variables. So for example, this Killing vector corresponding to time direction, as usual, gives us the Fourier mode for time. And then after that Fourier mode is put in, time decouples completely. So now we want to extend this to rotating cases. And in the case of the Kerr geometries, this is not a real picture. This is just some artist expression of the rotating black hole. So in the rotating black hole, as one can see from this picture, we have the time translation. We have the rotation invariance in the plane. But this leaves two coordinates. And by just counting those symmetries associated with scaling vectors, we see they're not sufficient to fully separate variables. So we can get this dependence on phi and t because of the killing vectors, but the other two coordinates would generically be mixed. But what was realized by Carter in 1968 is that if you write things in appropriate coordinate system, so-called Boyer-Lindquist coordinates, then the equation for the scalar also separates. And that looked a bit surprising because there are no geometrical, no killing vector symmetries that are associated with the separation. Then later it was realized that the separation is associated not with a killing vector, but with a killing tensor or with a killing Yano tensor. So this y is a generalization of the killing vector that I wrote before. It has two indices and it satisfies this equation. And again, this tensor, more general versions of these tensors will appear later on. So that's nice story for the scalars. But if you talk about photons and gravitons, then another question arises: which components should separate? So even if we know that the right coordinate system is a coordinate system with r and theta, we still have to say which component of the electromagnetic field separates. The answer to that question was given by Tucholsky, and this answer was based on so-called Newman-Penrose formalism, which comes from rewriting equations for all fields in terms of gauge invariant objects. So in the Newman-Penrose formalism, one introduces frames. So these are 4 frames, and L, M, and M. And there's also frame M bar because frame M is complex. So the metric can be written in this frame like so. And then you have the 2 frames which functions of only R and 2 frames which are functions of only theta, apart from the prefactors. So this prefactor mixes everything together. The sigma also mixes everything together. But if you take out the prefactors, then in L and N, you have only functions of R. And in M, you have only function of theta. So this is a very nice property of the frame. And then the gauge fields in that frames. So once we define these 4 null frames, the gauge fields are encoded by 3 complex scalars. So you take the anti-symmetric tensor F mu nu and you expand it in the basis of the frames. And of course, it's real, so one needs to end complex conjugate. But then we have 3 complex scalars: phi 1, phi 2, and phi 0. So for any background, if you write the Maxwell's equations, you get the first order partial differential equations for these 3 fields. And the remarkable property of the Kerr geometry is that those equations are actually separable. And in particular, they separate for phi 0 and rho bar squared times phi 2. So that was a great discovery of Tucholsky. And in that series of papers, he also did the separation of equations of motion for graviton in the similar fashion. But it has a couple of problems. So one problem, which might not be such a big one, is that there is one remaining equation which remains non-separable. It's also quite hard to recover the gauge potential. And a significant part of the Chandrasekhar book on black holes was about that recovery. So you can get the field strength fairly easily, but in order to recover a gauge potential, you have to work hard, but it can still be recovered. But more importantly for us is that the construction is based on studying F and F dual, and specifically the self-dual and anti-self-dual parts of F. And that's very peculiar to 4 dimensions. So if you take any dimensions higher than 4, then a dual F star F is not even a 2 form, and you can't really talk about dual and anti-self-dual, self-dual and anti-self-dual configurations. So if you want to extend this to beyond 4 dimensions, it's good to modify this technique in a way that's not specific to self-dual and anti-self-dual parts. So perhaps one can solve these problems, and this way one can guess what happens in the dimensions higher than 4. So that question was addressed in this paper I wrote in 2017. And the story started with analyzing the explicit solutions for the gauge field. So the original expressions are quite complicated, and they were written in the Chandrasekhar book. But then if you construct frame components and you massage the expressions a little bit, then one finds that the projections, so the A's themselves are quite complicated, but the projections are not that bad. And in particular, there is this non-separable function, which existed already in Tucholsky case, and then it propagates to the gauge potential. But the separable part is fairly simple. So what happens in the separable part is that you have the separable function, and your projection of A on a given frame is proportional to the directional derivative along that frame. And then there are different coefficients of proportionality. So in the case of L, this coefficient depends only on R. In the case of N, it also depends only on R. And in the case of M and M bar, this coefficient of proportionality depends only on theta. So this observation leads to a guess, which might work, might not work. But it's a new separable ansatz. It's not the same as the Tucholsky one, but it's motivated by it in spirit. So we drop this part. And instead, we just say that the projection of A to frame L is equal to the directional derivative along the frame L of some scalar times a function of R only. And this function R function G plus is undetermined. So similarly, you do for N with some other function. And for frames M, you also do it with with two functions, F plus and F minus, which are now functions of only of theta. And for psi, you require that it is separable. Again, this is ansatz. It may work, it might not work. And fortunately, it did work. But in order for it to work, one needs to fix this function G plus, G minus, F plus, and F minus. They cannot be arbitrary. And it turns out that they're completely determined in terms of one parameter mu. So this mu here is a free parameter. Everything else is fixed in terms of the coordinates. So c theta here means cosine of theta.
Excuse me, I have a question.
Please go ahead.
Yeah, so I somehow miss the 2 degrees of freedom of gauge field, right? Massless gauge field should have 2 spin components, and you have only psi. So does it
Yes.
mean?
Okay. Good. This is an excellent question. I'm going to address it in a couple of minutes, and if I don't, please interrupt. This is an excellent question. Actually, all polarizations are recovered. But if I don't address it fully, please ask again. All right. So, so we have these functions f and g, and they're completely determined in terms of the metric, apart from this single parameter mu. And then, if you go to the Maxwell's equations, so you substitute this to the Maxwell's equations, one gets a separable system of equations for R and S. So this is an example. This is the equation for S. And then there is a similar equation for R, but you see that S does not contain R variable. And similarly, equation for capital R does not involve theta variable. So it turns out that this equation is the same, or same in spirit for the scalar. And the only difference in the scalar is that there are these coefficients, D's. In the case of the scalar, you will have to put these coefficients to be 1. So let's say here you have d theta, which is equal to 1, and your lambda is a free parameter. So there is one separation constant, as it should be, and that's how it works for the scalar. In the case of the photon, these d's are actually fixed. So they're not equal to 1. They fixed as the fixed function of r and theta. But your lambda now has no freedom. So essentially, you're treating this, you trading this free parameter lambda in the scalar equation for free parameter mu in the vector equation. And now coming to the question about the number of polarizations. So for given mu, it looks like there's only one function. But you actually have this mu could be any real number. And as you vary that mu, you find that you find basically a family of those solutions. But then you can show, and that was shown in the paper, I'm not going to discuss it in detail, but what you can show is that any two values of that parameter can be used as independent ones. So for example, you can take mu equals to 0 and mu equals to 1. And then everything else can be constructed as a linear combination of these two. So, so this polarization, which was asked about, is encoded in this mu. And you can show that it's not a continuous family of polarizations, but actually two polarizations, and everything else are linear combinations. Dmitry, did this answer the question?
Yeah, but I just missing what is mu. It enters non-linearly into the equation, but you restore the linear yeah, so linear space of solutions.
Yes, no, that's highly not. I'm certainly not doing the exercise, but it's highly non-trivial. But what you can show is, if you take one value of mu and you take some other value of mu, then solutions are linearly independent.
Okay.
Now, the moment you bring in the third value, you can actually show that that solution can be built from the other two.
Okay.
Linearly.
Okay.
Again, I'm just giving you the result, but it's a non-trivial calculation. There's a whole appendix about it.
Thanks. Yeah.
Okay. Thank you. All right. So so now this is just a reformulation of the four-dimensional case, which has this great advantage that the gauge field enters algebraically, and also we never use the self-duality condition. But the question is, can this be extended beyond 4 dimensions? And can it be extended to other fields? So that brings us to the discussion of the Myersberry geometry. So in general, so Myersberry geometry is a d-dimensional generalization of the curve geometry. And as you go to higher dimensions, you're going to find more rotation parameters. So specifically, if you get d dimensions, there are d minus 2 integer part of d minus 1 over 2 rotations in those dimensions, and the structures are different between odd and even dimensions. So in this talk, I will focus on even dimensions, but the work was essentially done in parallel, and there are structures for odd dimensions and for even dimensions, but one really needs to discuss them separately because the Myersberry geometry looks very different in odd and even dimensions. So you have the total number of, let's say if you take total even number of dimensions, 2n plus 1, then because of these rotations, you have that much symmetry. So this u1 to the n is coming precisely from those rotations. And these are the Killing directions analogous to phi. Then you have the time translations. And this allows us to split n plus 1 dimensions. So n dimensions from here, 1 dimension from there. But n plus 1, other remaining n plus 1 dimensions still remain coupled. However, it turns out that the scalar equation is still separable. Scalar equation and the Dirac equation are still separable because now there are families of those Killing-Yano tensors. And this was done in the series of work about 15 years ago. So one finds this Killing-Yano tensors with multiple indices now, not just 2 indices. These are antisymmetric tensors. And it turns out that the entire family can be built from so-called principal Killing-Yano tensors. So you can build it from this tensor of rank 2 using this very simple construction. So you take this tensor of rank 2, you multiply it by itself using the wedge product. It's rank 2 tensor, so you can multiply it as many times as you want. So you multiply it k times, and then you take the Hodge dual. So this gives you the Killing-Yano tensors of rank d minus 2k. And these things are constructed from the frames. So the frames are written here. And again, the interesting point about these frames is that each frame depends only on one coordinate. So there are these red factors, and red factors actually mix everything together. So here, for example, you can see, Arkady?
Yeah, I have a question, very naive question. So what's the relation to integrability of geodesics in a given background? Is there any relation of separability? For example, semi-classically, you may think that there might be some.
Yes, it's exactly the same story. So if you have this killing tensor, then it guarantees separability of both equations for geodesic and Klein-Gordon equation.
Okay.
And maybe the best way to see it, if you take a Klein-Gordon and you take the Iconal approximation,
Yes.
then you get the Hamilton-Jacobi.
Okay, so my question actually, now I could ask the second one. So suppose you have a string theory in a given background, like Schwarzschild, for example. And it's not integrable, but if it were, you may ask, what do you know about Vertex operators, which essentially are solutions of certain target space equations of motion, like graviton Vertex is like wave function is basically given by solution of linearized-Einstein equation or something. So at the level of massless states, that's a relation to which that's what we are discussing. So relation to the integrability of geodesics, because geodesics are just truncation of, classically it's truncation of string equations. But I just wonder, maybe there is some deeper connection still at the level of Vertex operators, though of course string theory is not integrable in Schwarzschild or in Kerr. But anyway, this was just side comment. But in some examples, like with Zumina-Witten, there will be connection with them, yeah, or lambda model, lambda deformation. There should be some.
Right. Yes. So I think this Hamilton-Jacobi is certainly necessary for integrability, right? Because if you take a limit, you reduce to this Hamilton-Jacobi.
Okay. Yeah.
But if Hamilton-Jacobi equation is integrable, so suppose you have a background where Hamilton-Jacobi is already integrable, would the full string be integrable or not? For that, I think you need to do some other additional analysis.
Yeah, that's not enough. Yeah.
Right, exactly. Right. So it's a necessary condition, but not sufficient.
Yes. Agree. Yeah. Okay. Thank you.
Thank you. All right. So so you have these things which are marked in red, and they mix all coordinates, but they just appear as a prefactors. But once you forget about the things in red, the rest here is a function of R only on the first line. The rest here is a function of only a particular coordinate xi. So these frames are in some sense separable frames because apart from these red factors, they just functions of only one coordinate. And then one can impose, one more thing is these coordinates x and r are some coordinates associated with the Myersberry geometry. But if you set the mass of the Myersberry to be 0, then you're just looking at flat space in some strange coordinates. And those coordinates are actually not that strange. They're simply ellipsoidal coordinates in the high dimensional space. So if you have flat space, you can introduce spherical coordinates, you can introduce hyperbolic coordinates, but you could also introduce ellipsoidal coordinates. And for m equals to 0, those are precisely ellipsoidal coordinates in flat space. So then, as was shown in these papers which I mentioned before by Frolov, Kubizniak, and so on, if you impose this ansatz for the wave function, then it works, and you get separable equations. This is just based on existence of the Killing-Yano tensors. But now we actually need the explicit form of these equations because we're going to compare them with equations for tensors and vectors, and so this were explicitly derived. But they were guaranteed to exist, but they were explicitly derived here. And the separation constants. So now you have not just one constant, you have n of them. And those separation constants are encoded in the polynomial P. So there's one polynomial of degree n-1, and that polynomial has n free coefficients. So here, this polynomial appears as a function of r squared. Here, the same polynomial appears as a function of minus xj squared. So you fix these n coefficients, and then they appear in all these equations. So these are the separation coefficients. And the question is, can we do this for fields with higher spin? And what would be the counterparts of those equations? So for the Myersberry, for the Maxwell's case, it was done again in this 2017 paper. And that's for the gauge field, was motivated by 4-dimensional constructions. So from the point of view, from the 4 dimensions, it looks like we need those frames L plus minus and M plus M minus, or M and M bar. Now we have frames, and to build those counterparts of L and M, we just combine those frames. So you take these two frames and you build the combination like so. And similarly, you take the I's frames and you build the combination, complex combination. So these Tucholsky's frame turned out to be eigenvectors of the Killing-Yano tensors in 4 dimensions. If you just take 4-dimensional result. Unfortunately, it was not really appreciated in Tucholsky's paper, but now we certainly know that's the case. And then we impose the ansatz inspired by 4 dimensions, exactly the same separation constant. But before we had only one set of m's, now we have many m's. N such m's, where n is, where dimension is 2n plus 2. So in the end of the day, things again work, and we get a separation, we get separable equations. So there are a system of ordinary differential equations. There's a polynomial of degree n minus 2 now. So once again, we are trading one constant in this polynomial for the separation constant mu. And if you count the separation constants, things work out nicely. There are n plus 1 angular momentum and energy. So n angular momenta plus energy. There are n minus 1 parameters in the polynomial and the parameter mu. So exactly this number of separation constants that you need to fully solve the problem. The equations for scalar and photon are very similar. You just have different d's. So in the case of scalar, d's are equal to 1 and arbitrary lambda. In the case of the vector, these are the d's, and lambda is fully determined. Odd dimensional case requires a separate analysis, but the results are similar. And finally, you could analyze the polarizations in the same way I described them in the Kerr case. And there are d minus 2 polarizations and d dimensions. So this solves the Maxwell problem completely. And now we're coming to higher forms. So as we know, string theory has various p-form potentials. And in 4 dimensions, they're not particularly interesting because you can dualize them back to scalars. But in higher dimensions, they give you some non-trivial dynamics. So in this paper, the ansatz, which was imposed, was like that. So we take the projection of the form on various frames. We require it to be proportional to the directional derivatives along those frames. And then there are prefactors. And the tricky part is precisely this set of prefactors. So in the case of the vector field, things were very simple. You just had a function of that particular coordinate. In the case of the tensor fields, after some guesswork and consistency checks, it was shown that this f is not a separable function, but it's essentially discriminant. So you take these various x's. So there are, I should probably explain the notation. So the notation here is mu is a space-time index. This I is the label corresponding to m, like m1, m2, m3, and so on. And alpha is just plus or minus. Because remember, we had these frames which were plus or minus frames. So that was this alpha. So the coefficients f here are obtained by taking product of the differences between different x's. And these h's, again, from the consistency conditions, must have this form. So there are two parameters, E2 and E3, which are free parameters. And then there is a parameter set of parameters Q, but they're not free. They're coming from solving algebraic equations. So again, this is a very important distinction between the P form of P greater than 1 and the gauge and the in the gauge field. That in the case of the gauge field, you just had the parameter mu, and that was it. Here, there is this piece that, and the coefficients q are fixed, but they depend on the frequency and on the angular momentum. This is a completely new phenomenon, did not happen for the Maxwell field, but it happens for all higher forms. That you have to solve this equation for coefficients q. And this is an algebraic equation. It has precisely p minus 2 solutions. And here you just take a product over all the solutions. And after that, it's guaranteed that the function psi satisfies separable equations. So this is a complicated equation, just to stress that it's known explicitly. So if you know the omega and all angular momenta, then everything in this equation is known and fixed apart from this polynomial of degree n minus 3. So again, counting the separation of counting separation constants, there are E2 and E3, two separation constants here, plus n minus 2 separation constants and minus 3, which is exactly the full set of separation constants that one would expect. So this separation ansatz works for Myersberry geometry with cosmological constant as well. Just for simplicity, I was focusing on the standard Myersberry, which solves the Einstein's equations in the vacuum, but for cosmological constant things work as well. And they also work for massive vector fields, at least. And so to summarize, there are separable solutions for all p forms in all dimensions in rotating geometries. So there is a similar ansatz which seems to be working for gravitational waves. And again, it's based on taking such projections, but that work has not been completed. And right now the equations are still somewhat complicated. So I'm not writing them down here. So now we're switching gears. And I'm going to talk about excitations of the WZW models. So I will discuss both gauged and ungauged WZW models. So the simplest ungauged one is this one. And the ungauged Weiss-Dominowitz model has no dilaton. So it has the metric, and the metric can be read off from this part. And it also has the Kalb-Ramond B field, which can be read from that part. So this is field strength, but the B field can be read from there. First, let's review the scalars on such geometries. If you have group manifolds, or if you have ungauged case, then there is a unique equation, and there are several U1 isometries. So if you have a group, then all U1 isometries will be preserved. Of course, we need commuting ones. So it's not, you don't have enough isometries to do the full separation, but there are still some. For the coset model, situation is a bit more interesting because there you have a dilaton, and there is an ambiguity in coupling to dilaton. So in principle, you can consider an entire family of scalar equations like so. If sigma is equal to 0, this is the minimally coupled scalar. If sigma is not equal to 0, you have some scalar with non-trivial coupling to the dilaton. And it turns out that sigma equals to 1 is particularly interesting because you could also analyze this problem from the perspective of worldsheet and construct the Hamiltonian, analyze its spectrum, and so on. And as was shown in this work in 2010, this leads to the set of the eigenvalues, which is given by a very simple formula. So if you have a G over H sigma model, coset sigma model, then you build the following configuration. You fix a representation of group G, which we call capital R, or not we, but Polychromatus Stephters. Then you take a representation of the subgroup H, which was called little r, and then construct the quadratic Casimirs. And then in the denominator, you put, if you have level k, k plus g, where g is the dual Coxeter number for group and the subgroup. So the spectrum for sigma equals to 1 then is completely solved using purely group theoretic techniques, and there is no separation of variables needed. And in fact, generally there is not. This, however, raises some questions. So what are the eigenfunctions? This is very nice that this PS got an eigenvalues, but what are the eigenfunctions? Is there a separation of variables at least for some groups and some cosets? What is the spectrum of vectors and higher forms? So this formula works only for the scalars, but what happens to other forms? What is the spectrum of sigma equals to 1? If sigma is not 1, then this technique does not work. And finally, can the results be extended to integrable deformations of WZW models? Now let me talk about the answers to some of those questions. So in this recent paper with G81, we looked at some separable situations. And we started with some simple examples where separation is essentially trivial, which is a case of the group model. So if you have a group model for SO4, which is SU2 cross SU2, then the metric is very simple for each SU2. So there are two killing directions for each of SU2s, two U1s there. And as a result, on each SU2, you have function of only one variable. So if you take about this left SU2, it's function of only y. If you talk about right SU2, it will be some function of y tilde. So then the separation is trivial, of course, because you have function of y and y tilde, and those don't talk to each other. In the case of the coset model, when you take a coset over SO2 cross SO2, so this again is a product space. Now this three-dimensional space reduces to a two-dimensional space. And you generate a non-trivial dilaton, because whenever you go gauge this Vezo-Minowitten model, the gauging procedure gives you a non-trivial dilaton. But again, separation works for trivial reason. There are functions of only y here. There are functions of only y tilde here, and then separation works trivially. What is with less trivial is that vector fields also separate. And starting with explicit components, we show that the most general separable modes are fixed in terms of 4 constants. Well, not 4, sorry. It's actually, 6 constants, because there is plus or minus. They fixed in terms of 6 constants. And all the separable modes can be written like that. So again, we see that the structure is the same as the one we saw in the black hole case. The projection of the gauge field on a frame is proportional to the derivative along that frame. And the difference between the black hole case is that before there were some prefactors, which were non-trivial functions of various coordinates. Here, all these prefactors are just constants. But other than that, it's exactly the same kind of structure. So another interesting full separable case, which is a bit less trivial, is the coset SO4 over SO2. So in this case, you gauge only one U1s. And this is actually diagonal. It's diagonal between this and that. And once you gauge the diagonal part, the metric no longer splits. So now these non-cyclic coordinates, this non-cyclic coordinate y and y tilde are mixed. There is also non-trivial dilaton, and there is also non-trivial B field. So in principle, separation of variables here is not guaranteed at all. But in order to see that it's there, one can observe that this coset is an intermediate step in the sequence of T-dualities. So if you start with this metric, on this full space, and you do a T-duality along the diagonal direction between SU2 left and SU2 right. So if you do that T-duality, then what will happen is you get a metric, you get a 5-dimensional metric, and then separately you get a 1-dimensional circle. And that 1-dimensional circle doesn't couple to anything, so you could just forget about it. You might keep it if you want, but you might also forget about it. So, so in that sense, going from here to there, you just do one T-duality and you forget about the remaining circle. If you do one more T-duality, then again the duality, the direction along which you dualized becomes a separate circle. And if you forget about it, you get the you get this you get this cosine. So it's intermediate step on these dualities. This case is separable, this case of separable. So perhaps we can use the T duality to argue for separability of things in the middle. And indeed you can. But in the middle, only equation for sigma equal to 1 is separable. And equation for any other sigma is not separable. And so that we checked explicitly, but also this is a nice consequence of T duality, because if you do T duality, then the metric changes and the dilaton changes. And it turns out that sigma equals to 1 is precisely the equation that remains invariant under this T duality. And only this equation remains separable. So if you look at the vector field, situation becomes even more interesting, because now you can, first of all, you can consider this parameter sigma in the vector field as well, but it gets fixed to sigma equals to 1 for separability. But also in the case of the vector field, you can define so-called twisted field strength, which is the standard field strength for the vector field, plus a contribution from the B field. So remember that now we have a non-trivial Karl-Bramon field, and you can add such pieces into your field strength. And it turns out that the vector equation is separable only for sigma equals to 1 and zeta equal to plus or minus 1. So if you add this part with any other coefficient, in particular if you don't add it at all, then equations are not separable. This is consistent with the general properties of T dualities, that if you have the Killing-Yano tensor before T duality, and you do the duality, then in general, Killing-Yano tensor will not be preserved. But what will be preserved is so-called twisted or modified Killing-Yano tensor, which is the tensor where the derivatives are defined not with respect to Levi-Civita connection, but with respect to Levi-Civita connection with torsion. And here, this plus or minus signs precisely would correspond to zeta equals to plus or minus in the equation above. So again, you take this separable solutions, and you can show that this gauge fields satisfy the same rule that the projection of the gauge field onto the frame is proportional to the derivative along that frame times some function of the coordinate. So now these b's become, here they were constants, now they become functions of the coordinates, but they're functions of only one coordinate. So if you take projections to the frame depending on y, they are functions of only y. If you take projections to frame depending on y tilde, the functions are only y tilde. And then there is one frame which mixes y and y tilde together, and this b is not a function of anything. So the separations, the conclusion then is that separations in the vector equations in the black hole and the Berzomino-Witten model follow exactly the same pattern. So now we go to larger groups, and in that case, separation no longer works. You could still do the partial separation. And in particular, if you look at the group model, so let's say you take some group G, then you can act on the group element by multiplying it by some constant group element from the left and some constant group element from the right. So then these things cancel out. So the entire sigma model has this G left cross G right isometry. In order to get separation of variables, we need commuting isometries. And in particular, we need commuting U1 isometries. And since SO5 has rank 2, you get 4 commuting killing vectors from this procedure. So you have G left, which gives you 2 killing vectors. You get G right, which gives you 2 commuting killing vectors. Altogether, you get 4. But the total space is 10-dimensional. So certainly, these 4 commuting killing vectors are not sufficient to guarantee full separability. And However, we managed to construct several infinite families of separable solutions that depends on 6 coordinates. So here you guaranteed that 4 coordinates decouple, but we managed to construct things depending on 6 coordinates. This is just some example. And the interesting structure of the example, so this is the simplest example, the more complicated ones, but all these examples have the structure that you have the U1 isometries, first of all. So these are these 4 commuting Killing vectors. And then there are 2 more directions. So in this particular case, it's this capital R and Y minus. I'm not introducing details of the coordinates, but there are certain coordinates in the system. And in all the separable solutions, the dependence on those coordinates appears in the form of the hypergeometric functions. So that's very nice, but it's still not a full separability. So if you want to find all eigenvalues and all eigenfunctions, that's not going to do it for higher groups. But we can probably get some understanding by analyzing this formula for eigenvalues and building the corresponding eigenvectors for it just from solving differential equations and algebraically. So why is it interesting? So first of all, if it's interesting because even in the sigma equals to 1 case, we will find the system of eigenfunctions. But more importantly, if you want to go beyond sigma equals to 1, then these PS techniques will not work. But maybe those algebraic techniques will work, and it will be possible to find the eigenvalues. And finally, if you want to go beyond the scalars, also this Hamiltonian does not work, and we need something else. So motivated by all of this, you can study eigenfunctions, and you can show that these eigenfunctions are built. All such eigenfunctions are built from the group elements by just constructing various Young tableaus and doing symmetrizations. So here there are these G's, which are elements of the coset. So here, if it was a group, it would be an element of the group, but otherwise it's an element of the coset. So we need to specify a representation of the group and representation of the subgroup. And then by looking at the corresponding Young tableau, you symmetrize. So here is the symmetrization over under second index. You do it according to the Young tableau. I'm going to give an example in a moment. So the only tricky part is because we're not looking at just representation of the group, we're looking at the presentation of the coset. It's very important here to distinguish the group indices from the coset indices and do symmetrizations according to a representation of both. In the SO6 over SO5 case and SO3 over SO3 case, which are most interesting from the string theory perspective, some polynomial structures were uncovered. And the extensions were also performed to the lambda deformed background. So first of all, even before you switch on any deformation, this is an example of such procedure a little bit more explicitly. Suppose you take the simplest Young tableau, which has only 1 block. Well, simplest after the trivial one. Suppose you have a Young tableau which has only 1 block. So if you also say that you don't put any subgroup indices, if all groups are group indices, then this procedure. So here, of course, there is no symmetrization or anti-symmetrization, it's just one element. So you read of the corresponding matrix element, and it is a polynomial in the variable 1 over y squared. If you take indexes on both, so if you here you say that this is Young tableau with 1 box, both for group and for the subgroup, then it's again a polynomial. But now there are more variables in that polynomial. So this x and alpha have certain coefficients in the metric, certain coordinates in the metric. But the important point is whatever you build has a polynomial structure, and we analyze the structure of those polynomials, the powers and asymptotic behavior and so on. And in the case of the group, you will find that this expression corresponds to the eigenvalue 12. This expression corresponds to eigenvalue 4 in accordance to this formula. Now, if you introduce lambda deformation, then representations with the same number of boxes start mixing together. So the representation with one box will mix together, but they will never mix the representation with two boxes, and so on. And the mixture matrix looks like this in this particular example. So this kappa is something that's proportional to the value of the lambda deformation. And then you just solve this very simple algebraic equation to find the corresponding eigenvalues and eigenvectors. So if kappa is equal to 0, in the undeformed case, you back to this case. But if kappa is not equal to 0, you just have to solve some simple equation. So that's nice. But again, the goal here would be to go beyond sigma equals to 1 and also possibly to extend things to vectors. And this work is close to completion. Just to reiterate, group theory arguments would not work until sigma equals to 1. So we need to combine, we basically need this kind of argument. You take these group building blocks and then you combine them according to certain rules. So in particular, looking at those polynomials, we found a very simple limit of the geometry that allows to build at least the eigenvalues in a very simple way. And just an example, in the case of SO4 over SO3, from the limit of that partial differential equation, we find a very simple expression for the eigenvalues. So these are all eigenvalues. If sigma is equal to 1, then this goes back to the group theoretic formula, because these two terms give the quadratic Casimir of the group. These terms give you quadratic Casimir of the subgroup. So in this case, the subgroup SO3, so at least that one is familiar. It's j times j plus 1. So here you call it little L1, just to agree with higher groups. But as you change the sigma, this is no longer such a simple Casimir, but it's a very simple extension. And we also have this extension for all the cosets. And then there is a similar expression for the vector field and for the other cosets. Again, this will be just very simple modifications of the Casimirs. So to summarize, the goal of this work was to look at equations of motion for various fields in black hole and WZW geometries and understand the role of symmetries in solving such equations. I started with talking about the new approach to the Maxwell fields in 4 dimensions. Such approach was needed because the traditional method gives a simple master equation, but Tucholsky's master equation, but it's very hard to recover the gauge potential. And also the construction is based on self-duality, so it's not clear how to extend it beyond 4 dimensions. The new separable ansatz allows to recover the gauge field algebraically, and more importantly, it's extendable to higher dimensions. So for all fields in the Myersberry geometries, I presented the ansatz for all forms, and they were based on eigenvectors of the Killing-Yano tensors. The universal separable equations for the scalar and the master field were obtained, and all polarizations with appropriate number of separation constants were recovered. For the Vezo-Minowat models, we found full separation of variables in low dimensional cases. And as a byproduct, this led to new examples of geometries with non-trivial Killing-Yano tensors. Those are few and far between, because Killing-Yano is a very rigid structure, and very few geometries preserve them. The separation of vector equation turned out to be very similar to the black hole case. So specifically, this ansatz, which was made here, was derived here as well. So here, one had to impose it. Here, because situations were sufficiently simple, we analyzed the most general separable solution, and we showed that it fits that ansatz. But beyond these low dimensional cases, there is probably no separability, and one needs an algebraic construction of eigenvectors and eigenvalues for various groups and cosets. And in particular, we have finished this work, should appear soon, for the SON plus 1 over SON coset. And finally, all of this is interesting because this light modes probe dynamics of stringy geometries. So once the solutions are obtained, one can analyze scattering amplitudes and things like that, and extract the information about the corresponding string theories. Okay, that's it. Thank you.
Thank you. Are there any questions?
Are there any examples where you have Ramon flux in the background? For example, you discussed Veseminovic models have B flux, B field. You can consider as dual of that, and that would be non-trivial if, for example, if there is a dilaton. Well, for gauge Vesemino models, if you consider as dual, that will give you some somewhat different background. Where you'll have Ramon 3-form and dilaton coupled differently. I'm just asking. I guess as duality is just SL2R symmetry in supergravity, so it's not really, it will not give you something interesting about some new information about the background, but fluctuations are different. So SL2R will not act probably what I'm saying, probably not right what I'm saying, because still it's a symmetry of full equations, so it should be symmetry of linearized equations as well. Yeah,
it might map different one set of modes to a different set of modes.
Yes, but it's still, yeah, it will still be not changing the fact about.
Right, good, but still this is very good, because suppose you started with 1 form, and if you do T-duality, it might go into 2 form. So suppose you manage to separate the let's say the vector equation, then after T-duality, I guess it will be guaranteed that something is separable, but that something might not be vector equation anymore.
Yeah.
It might be a 2-form equation.
Okay, yeah, but anyway, this is a bit abstract question. It's just, yeah, in principle, what could raise this question if you're given some solution of, say, some supergravity, not in 4-dimensional, but in, say, 5 or 6, where these fluxes, where Ramon fields play also some role in the, for the solution. So you may ask about separability. For example, D3 brane, you can consider D3 brane solution and ask that question. Fluctuation on top of D3 brane solution.
Right, for the scalar, that's actually what we looked at with Yuri some years ago. When we discussed this modified Kilian tensors, we also looked at scalars on various black hole backgrounds, and these were charged black holes. And those did have Ramon fluxes.
Okay.
But only for the scalar. I've never looked at anything, and I don't think anybody looked at things with Ramon fluxes and vectors, for example.
But again, you can look at different scalars which couple to, well, scalars which may be coupled to dilaton.
Dilaton, yes.
Yeah. Okay, thank you.
Thank you.
Other questions? Did I understand correctly that you are mostly interested in massless fields?
Here, yes.
And why is that? Can you do the same for massive? Scalar, massive, spin 1.
Oh, okay. Yes. Yes. So certainly it works for massive scalar as well, and it also works for massive vector. So I guess the reason I was thinking about massless fields mostly is because you have a lot of stringy modes, and those stringy modes couple to different fields, background fields in different ways. So if you look at supergravity fields, at least you know the couplings. If you start looking at massive fields, you also need to say how things couple to the other fields, to the other background fields.
Okay, I see.
Right. So in other words, if you have a vector, suppose you have a vector, and as Arkady said, suppose you have some background Ramon flux. What is the action you would be writing for the vector? The simple thing would be just to have a minimally coupled vector, let's say, which does not see the Ramon flux, but it's not clear that's the most interesting one.
I see. And another thing, so maybe, like people well, use extensively this double copy construction to construct geometries, but I don't know, maybe it's also useful to construct some sort of plane wave solutions in these geometries. Doesn't make sense to try to scatter, to like double copy an electromagnetic field in this background to get gravitational excitations.
Yeah, it could be useful. I looked at it at some point, but I never. It's certainly an interesting thing to consider, but I could not get anything practical out of it. Which is not to say it cannot be done.
Yeah, I see. Yeah, there was some papers maybe like about solutions in plane wave backgrounds, where people use some kind of tricks first to have these solutions and then to square them.
Right.
But okay, so maybe it's not very relevant.
Yeah, I think when people build solutions, they usually don't depend on all coordinates. They depend on only on some subset. Like here the goal is to build things with the maximum number of separation constants.
Okay, thank you.
I have a kind of strange question. What about high spin fields, massless high spin fields? I have vague reminiscences that probably there were some discussions of high spins. For example, on a Ricci flat background, you can consider equations for whatever massless graviton, but you can also consider massless spin 3, spin 4. And they will be formally what, consistent? Maybe not. Yeah, if we put cosmological constant, yes, maybe.
I'm afraid that it's only consistent in Minkowski and ADS. That's it.
Yes. Okay. Yeah.
But yeah, cosmological constant is fine. You could just have this Myersberry.
Yes, but then yeah, indeed, we don't really know exact. Yeah, what's the analog of? Yeah. Yes. So there will be no good. Well, you can look for some self-view. Yeah, I don't know. It's not well-defined question. Yeah, sorry.
No, but it is interesting because at least formally you can write those equations, and if cosmological constant is negative, you can probably, they would even make some sense physically. So
the question is really about gauge invariance. Yeah, you can formally write these equations, but consistency, whether you have the same gauge invariances in flat space or on ADS or DC, that once you put it in Ricci flat space, once you put it, say, in Schwarzschild, that would be the
yes, right.
issue. Yeah. But you can certainly do gravitino, for example, but that will be supersymmetry related to graviton,
Right.
I guess. Yeah.
Well, except that these backgrounds are not supersymmetric.
Yes. Well, does that really matter? Yeah, you can consider Ricci, you can consider Schwarzschild and do supersymmetry transformation on it.
Okay, yes, that's right.
So formally, you can probably do that. Yeah, like looking at this as solution of supergravity. Yeah. Okay, thank you.
Also, you say you just don't even have to solve equations. You just take the supersymmetry variation. You get some kind of. Oh no, wait. But I think then you get a gravitino with very specific dependencies, because it would be just some small variation of the Schwarzschild solution or Kerr solution, which did not have any time dependence and phi dependence to begin with. So this would probably mean that your gravitino will have a very specific time dependence and very specific phi dependence. Like
what's the discussion of killing spinor instead of killing tensors, some whatever spin tensors or something like that?
Yeah. Okay. So yeah, you can consider killing spinors, but if there are killing spinors, then there will be supersymmetries.
Yes. Well, that's a different story. Yes.
Right. Yeah. So there are backgrounds which admit killing spinors, and there are backgrounds which admit killing Janus, and somehow there is not much overlap between the two.
Okay.
Any other questions? Okay, if there are no other questions, so let's thank the speaker.